Good morning, everyone. This is lecture 16. And what we are doing is beginning is the new chapter, chapter 4, on applications of the derivative. So we have a function. Maybe let's define like this, from x equal a to x equal b. And we have, this is the graph of the function, y equals f of x. And we're interested in two kinds of points on the graph of a function. Like this is called an absolute maximum. A point like this is called an absolute minimum. So let's say this is the point C. X equals C is an absolute maximum of the function f of x on the, in this case, closed interval, square brackets AB. So this means the set of all x greater than or equal to A and less than or equal to B. If f of C is greater than or equal to f of x for all x in this closed interval. So as you look at the graph of the picture as I've drawn it, here at the point x equals c, the function is bigger than it is anywhere else in this interval. And it's just, and we say absolute maximum with respect to a specific interval. And outside that interval, the function can get very large, very small, but we're only looking at the function in this interval. So that's an absolute maximum. And similarly, there's the idea of an absolute minimum. So we say that x equal d is an absolute minimum of the function f of x on this set AB, the closed interval from A to B, if f of d is less than or equal to f of x for all x in AB. And typically an absolute minimum or absolute maximum looks like that. You could also have, let's say we had a parabola looking like that. But we're only looking at the interval this is say A and this is B. So here we have the graph of a function, and on this interval, so from A to B, at x equal A, you absolutely have an absolute minimum. The function is smaller to the left and even smaller when you get a little bit far enough to the right. But on this interval from A to B, this is absolutely the smallest value the function takes on. So this would be an absolute minimum on the interval from A to B. And again, it's clearly specific to the interval. It's much smaller when you go to the left of A, but if you're only looking in this region, that's the smallest the function gets. And there's a fundamental fact about absolute maximum and absolute minimum. These are sometimes called extreme values. So this is stated in the text as theorem. 4.1. Function that is continuous on a closed interval AB always has an absolute maximum and also an absolute minimum inside the interval. So in this case, here's an absolute minimum, here's an absolute maximum. And this statement is very important in mathematical analysis, but it's specific to closed intervals. It's not true in an open interval. So to give a very simple example, so we have the open interval. In general, an open interval AB means all x which are strictly greater than A and strictly less than B. It doesn't include the endpoints. So on the open interval, from 0 to 1, the function f of x equals 1 over x has no absolute minimum or absolute maximum. So what does the graph of this function look like? From 0 to 1, as you approach 0, f of x equal 1 over x goes to infinity. And even as you approach 1, the function is getting closer and closer to 1, but it doesn't hit 1. As you approach 0, the function is actually shooting up to infinity. So it has no absolute maximum. So this statement about the existence of an absolute maximum or absolute minimum is true for closed intervals. It could also be true in special cases for an open interval, but it's not true in general for an open interval. So that is a useful fact to keep in mind. Now, what is perhaps more important than absolute maximum and absolute minimum are what are called local maxima. Is Latin, so the plural of maximum is maxima, and the plural of minimum is minima. So local maxima and minima. I mean, you could have a function, even say on the interval from A to B, which looks like this. And if we look, for example, at this point, sorry, maybe this is a better example. At this point is what is called a local minimum. So the function is not smaller here than it is everywhere else in the interval, but if you take some little neighborhood around that point called the C, and for values of x close to C, f of C is less than or equal to f of x for all x such that, let's say, x is less than c plus delta and greater than c minus delta, for some, no matter how small, delta greater than 0. So this would be the point c minus delta. This would be the point c plus delta. And we're looking at that interval. And in that interval, the function is smaller there than it is anywhere else. Similarly, this point, let me draw a better picture perhaps. Let's say this is A and this is B. Here's a point, I'll call this point D. So this is not, at this point, the function f of x doesn't take on the largest value anywhere in the whole interval, but x equal d is a local maximum if f of d is greater than f of x for all x, such that x is in some small interval, x d plus delta, d minus delta. So there's some small interval around that point, and in that little interval, that local neighborhood, the function is bigger, has a higher value than it does anywhere else. And in the process of trying to understand the shape of a function in some interval, one of the first useful bits of information you can find is to find the local maxima and the local minima. That tells you where the function is going up. And right. Is there a question about any of this? You should mute yourselves during the talk. Someone asked in the chat how much the first exam counts toward the grade. Originally, I thought I would have just one midterm exam, but the grades on the midterm that I just gave were not very good overall. And so I'm going to be giving a second midterm, and I'll send out I will post on Blackboard how much each midterm will now count. But I want to give people a chance to improve their grades. So there will be a second midterm sometime end of April, very beginning of May, most likely. Okay. Well, we've been studying derivatives and what is the connection between derivatives and local maxima and local minima. And that is stated in the very important theorem (4.2). If you have a function f of x, and if it has a local maximum or minimum at the point x equals c, and if the derivative at c exists, then the value of the derivative is always 0. And let's just note, let me recall, a critical point of a function f of x is a point C, and there can be many, such that either f prime of C, the derivative exists, and f prime of C is equal to 0, or f prime of C does not exist. So if you have a function like f of x equals the absolute value of x, the graph of that function looks like that, and there's a sharp angle at x equals 0. There's no derivative here, so x equals 0 is a critical point because it's a point where the derivative does not exist. Everywhere else, for x greater than 0, the derivative exists and is equal to 1. For x less than 0, the derivative exists and equals -1. So this function never takes on, the derivative of this function is never 0. But there is one point where there is no derivative, and at that point, x equals 0. The point x equals 0 is a critical point. So this is a curious definition in a sense. You have a critical point wherever the function has no derivative, or where the derivative is 0. And in particular, if you have a local maximum or a local minimum, the derivative is always going to be 0. Let's look at the proof of that. So suppose we have a local maximum, say at x equals c. So suppose x equals c is a local maximum. That means that if, so that means that f of x is less than or equal to f of c for all x between, let's say, some interval c plus delta and c minus delta. So there's some interval. And in that interval, f of c is bigger than or equal to f of x. That's the local maximum. So if you take a number h between c and c plus delta, f of c plus h minus f of c divided by h, what can we say about that? Sorry, this is c plus h. F of c plus h is less than or equal to f of c, because f of c is a local maximum. So f of c plus h minus f of c is negative. Sorry. F of c plus h minus f of c is less than or equal to 0. So that means that f prime of c, if we take the limit of f of c plus h minus f of c over h, as h goes to 0, but through positive numbers, each of these numbers is less than or equal to 0, so the derivative is going to be less than or equal to 0. On the other hand, if I take an h, let me write it as c minus h, f of c, well, or let's say h is negative, that's better. F of c plus h minus f of c over h, if h is less than 0, f of c plus h, again, is less than or equal to f of c, but h is negative. So, sorry, so this is less than or equal to 0 over h, but h is negative. Say this better. I look at this difference quotient. f of c plus h is less than or equal to f of c. So f of c plus h minus f of c is less than or equal to 0. But h is strictly less than 0. So if I divide this by h, that changes the sign of the inequality. This is greater than or equal to 0. So if I take f prime of c, which is the limit of f of c plus h minus f of c over h, as h goes to 0, but through negative numbers, this is going to be something positive. So if we have a local maximum, the derivative is less than or equal to 0. It's also greater than or equal to 0. And the only number that satisfies both inequalities is 0. So that's a proof that at a local maximum, if you have a derivative, the derivative is 0. Actually, there's another way to see that, which is also very nice geometrically. So suppose you have your function and you have a local maximum. So if you take a point to the left, this is x equals c. This secant line has positive slope. So as you take your secants getting closer and closer to this point C, the slopes are always positive. So the limiting slope will never be negative. It'll be greater than or equal to 0. On the other hand, if you go to the right, the curve is going down, the secant has negative slope. And if you take the sequence of the slopes of these secants as you get closer and closer to x equals c from the right, you have to have something less than or equal to 0. And again, the only number that is both less than or equal to 0 and greater than or equal to 0 simultaneously is 0. So this gives us an algorithm, a method to find local maxima and local minima. Either the derivative does not exist at those places, or the derivative equals 0. So you have to look at the critical points and see what's going on. Now, let's take a couple of simple examples. Suppose I take the curve f of x equals x cubed minus 3x. Or like x cubed minus 9x. And we want to see, for this curve, find the critical points. And find the local maxima and local minima. So this function is a polynomial. It has a derivative everywhere. So there are no points that are critical points because the derivative does not exist. There's always a derivative. But what is the derivative? So let's say f prime of x is 3x squared. Let me change this. Let me make this 12 just to get an easier number. Be 3x squared minus 12, which is 3 times x squared minus 4. And that equals 0 exactly when x squared equals 4, or x equals 2, or x equal minus 2. So these are the critical points. These are the points where this derivative is equal to 0. Let's see, what is f of 2 equal to? It's 2 cubed minus 12 times 2. 8 minus 24 is minus 16. F of minus 2 is minus 2 cubed minus 12 times minus 2. That's minus 824, which is plus 16. So for this function, at x equal 2, the function takes on the value minus 16. At x equal minus 2, the function takes on the value plus 16. And this, in fact, is a local maximum. And this is a local minimum. The graph of this curve has a shape that looks like that. And here, local max. Here, local min. So here we have a case where the function has two critical points, plus 2 and minus 2, where the derivative is 0. And in fact, each of them is an extreme value of the function. One is a local maximum, one's a local minimum. It's very important to always remember that the converse is not true. You can have a critical point, but not have a local maximum or a local minimum. A simple example is if I take the cubic f of x equal x cubed. What is f prime of x? 3x squared. That's equal 0 when x equals 0. So this function has a critical point at x equals 0, but the curve f of x equal x cubed looks like that. And here at the point x equals 0, you have neither a local maximum nor a local minimum. Curve comes up, flattens out momentarily, and then continues to go up. Are there any questions about this? This is really fundamental to our study of calculus. Now, if you want to find the absolute maxima, absolute minima of a function on an interval, so you have the interval from A to B, you might have a graph of a function that looks like this. Now, at this point, you have a local maximum. At this point, you have a local maximum. At these 2 points, you have local minimum. But none of these 4 points is the absolute max or minimum of the function. The absolute minimum on this interval is actually right here at the endpoint. And the absolute maximum is right here at this endpoint. So, but this does tell us what we have to do when we're trying to find the absolute maximum or absolute minimum of the function on an interval. You check the critical points, the points where the derivative is 0 or does not exist, but then you also have to check the value of the function at the endpoints of the intervals. And that will always, if you can do the calculations, that will always give the absolute extreme values. Let's look at some examples. Suppose I take the function f of x equal to x to the 4th minus 2x cubed on the interval from minus 2 to 2. So what are the critical points? Those are the points where the derivative is 0. What is the derivative? F prime of x is 4x cubed minus 6x squared. So I can factor out a 4x squared, and I get 4x squared times x minus 6 over 4, or 3/2. So the critical points, this equals 0 at x equals 0 and x equals 3/2. So if there's a relative or a local maximum or minimum of this function in the interval from -2 to 2, it'll be at one of these 2 points. But to find the absolute max and min, I need to find for these values, I have to check for different values of x, compute f of x. So what are the values of x that I have to check? I have to check the 2 critical points, 0 and 3/2, but also the endpoints of the interval, -2 and 2. So this is my function, x to the 4th minus 2x cubed. F of 0, 0 to the 4th minus 2 times 0 cubed is 0 minus 0 is 0. So at 0, this function has the value 0. What about a 3/2? F of 3/2 is 3/2 to the 4th minus 2 3/2 cubed. So let me calculate that. I'll try and do it the easy way. I'll factor out a 3/2 cubed, and I get 3/2 minus 2. So 3/2 cubed is 27 over 8. 3/2 minus 2 is -1/2. So this is minus 27 over 16. That's the value of the function at 3/2. The value of the function at 2 is 2 to the 4th minus 2 times 2 cubed is 16 minus 2 times 8 is 0. The value of the function at -2 is minus 2 to the 4th minus 2 times minus 2 cubed. This is 16 minus 2 times minus 8 plus 16 is 32. So what's the largest value this function takes on? 32 in this interval. And the smallest value is minus 27 over 16. So in the interval from -2 to 2, the absolute maximum is 32 at x equal -2, and the absolute minimum is minus 27 over 16 at x equal 3/2. Any questions about this? Let's look at another example. So this is a simple example about the motion of a particle. So suppose at time t, f of t is the height of a stone that's thrown vertically upward above a bridge. And f of t at time t is given by the equation minus 16t squared plus 64t plus 80. So we're tracking a particle as a function of time. This is the height. At t equals 0, you're 80 feet above the ground. And this particle is thrown upwards. So it goes up and it starts to come down and eventually hits the ground. And it gets to some maximum height. There's a local maximum for the, or an absolute maximum for the trajectory of this function, of this object that is thrown from the top of an 80-foot bridge. we want to find the maximum height of the stone. So we're looking for a maximum value of the function in this interval. So we compute the derivative f prime of t is minus 32t plus 64. That's equal to 0, and t is equal to 2. And we also have the endpoints of the interval. So, and what is the height at time 2? F of 2 is minus 16. 2 squared is 4, minus 16 times 4, plus 64 times 2 plus 80. That's minus 64 plus 2 times 64 is 64, plus 80, that's 144 feet. So at time t equal 2, it's 144 feet above the ground.
I have a question.
Yes, go ahead.
How did you find 2 for the t value?
So this is the function that describes the particle's height. Minus 16t squared plus 64t plus 60. We want to find, and this is what the trajectory looks like. You throw it up in the air. This is height as a function of time. It goes up, and then it turns around and starts to fall down. And we want to find this point, the local maximum, where it has its greatest height. You have a local maximum where the derivative is 0. That's what we've been discussing. Local maxima and local minima occur where the derivative is 0. Here's the function. If you differentiate this function, you get minus 32t plus 64. When is that equal to 0? When t equals 2. So this doesn't say that t equal 2 is a local maximum, but it does say that if there is a local maximum, it will occur at t equal 2. And in fact, that is the case because this is really just a parabola opening downward. So we know it does have a unique local maximum, actually an absolute maximum. And we just found it. Does that make sense?
Yeah, thank you.
So I want to state 2 very fundamental results about derivatives and local maxima and local minima. I mentioned these last week, but I want to mention them again. You can't talk about them too much yet. So there are 2 results. Better. Rolle's theorem. And the second is the mean value theorem. And one very simple way to say what Rolle's theorem tells us is the idea that what goes up must come down. So suppose we have a function defined on the interval from a to b, and there's some number where f of a and f of b, and for this function, they're equal. So if we're graphing this function at x equal a and at x equal b, the value of the function is the same. So what does the graph of this function look like? It starts here and it ends here. So no matter what happens, whether it starts going up or goes down, it has to end up at this point. And Rolle's theorem says that if f of x is a function which is continuous on this whole interval closed from a to b, and we have a derivative f prime of f of x exists, at least on the open interval from a to b, we're not requiring that it's differentiable at the endpoints, then the derivative has to be zero somewhere between a and b. So f prime of c is equal to 0 for some c in between a and b in the open interval from a to b. So if you start going up, at some point you have to turn around and come down, so you're going to end up at this point. A better picture might be something like that. Here, A, B, this is the f of A equal to f of B. Somewhere if you start here and then you end up at the same level, your graph has to turn around. If it starts going up, it's going to have to turn and come down. If it starts going down, it's going to have to turn and come up. But that has to happen. I don't think I'm going to prove this formally, but it's important just to see what's going on. That is, if you're going to start and stop at the same heights, if you start going up, then you have to turn and come down, and the point where you turn is the local maximum. You start by going down, at some point you're going to have to turn and come up, and that point where you start, turned around is a local minimum. Let's take an example. Suppose I have the function f of x equal to a certain cubic, x cubed, minus 7x squared plus 10x. I can actually factor this polynomial. I can factor out an x. I get x times x squared minus 7x plus 10. And I can factor this. This is x times x minus 2, x minus 5. So if I were graphing this polynomial, it's equal to 0 at 2, at 0, at 2, and at 5. So for example, so this is 0, 2, 5. F of 0 equals f of 2. So if f of 0 equals f of 2, the derivative has to be 0 somewhere between 0 and 2. This is my function. What is the derivative? F prime of x is 3x squared minus 14x plus 10. All right, if I differentiate it correctly. And I'd like to know, when is this derivative equal to 0? Well, you have to solve this quadratic equation. So this equals 0 when x is, what's the quadratic formula? Minus b plus or minus the square root of b squared minus 4ac all over 2a. So minus b is 14 plus or minus the square root of b squared minus 4ac. A is 3 and c is 10, so 4 times 30. That's 14 plus or minus the square root of 196 minus 120. That's 14 plus or minus square root of minus 4. That says that this polynomial has no derivative. There's no critical point. I don't know, let's just check. 3x squared minus 14x plus 10 equals 0. So x is minus b plus or minus the square root of b squared minus 4ac over 2a over 6. I was puzzled why I get a square root of a negative number here. 3x squared minus 14x plus 10. B minus b plus or minus the square root of b squared, that's 196, minus 4ac, 4 times 30, over 6. So something here is not right. This would be 14 plus or minus 2i over 6, or 7 plus or minus I over 3, but I should not be getting a complex number. Oh, actually, I can't do that. I'm not subtracting right. This is 14 squared, I said, is 196. Minus 120 is, I don't know what I got. I thought that was 200. Is 76. That's right. So let me just do this again. So it's done correctly. So if we have this quadratic equation, x is minus b plus or minus the square root of b squared minus 4 times a times c over 2a. So that's 14 plus or minus the square root of 196 minus 120 over 6, which is 14 plus or minus the square root of 76 over 6. 76 is 4 times 19, so this is 14 plus or minus 2 times the square root of 19 over 6, which is 7 plus or minus root 19 over 3. And you can calculate this numerically, and this is roughly either if you take the positive sign or the negative sign. Take the positive sign, this is 3.79. Take the negative sign, this is approximately 0.88. So that gives us the local maxima and local minima for that cubic curve. Okay. Always good to learn how to do arithmetic correctly. Finally, I want to say what is the mean value theorem. So the mean value theorem says something like this. Here we have a curve, and let's say this is the graph of the curve from A to B. So if I construct the tangent, the secant line, joining the curve at the endpoints of this interval, this is the point A comma f of A, and this is the point B comma f of B. And I claim that one way to describe this is that at some point on the curve, there's a point where the tangent line is parallel to this line. What is the slope of this line? The slope, well, this is just a straight line joining 2 points. So the slope is f of B minus f of A over B minus A. And I claim that there exists a point C in the open interval from A to B where the tangent line to the curve has slope parallel to the secant line. The slope is f prime of C. The derivative gives you the slope of the tangent to a curve at a point. So there's a point C such that f prime of C is equal to f of B minus f of A over B minus A. Another way to say that is that B minus A is equal to f prime of C, f of B minus f of A, for some C between A and B. And that is the statement of the mean value theorem. Let me look at an example to try to make this a little bit more concrete. Suppose we have the function f of x is 2x cubed minus 3x plus 1. And I want to look at the interval from minus 2 to 2. So what is the value of the function at 2? F of 2 is 2 times 2 cubed minus 3 times 2 plus 1. 2 cubed is 8 times 2 is 16 minus 6 plus 1 is 9. F of minus 2 is 2 times minus 2 cubed plus 3 times minus 2 plus 1. That's minus 16. Should be a minus. Plus 6 plus 1 is minus 9. Oh, 16 minus 6 is 10 plus 1 is 11. So what is the slope of the chord? So again, we have a curve. Say it looks like this. Here, and this is the point minus 2, minus 9. This is the point 2, 11. And what is the slope of this chord? 11 minus minus 9 over 2 minus minus 2. 11 plus 9 over 2 plus 2 is 20 over 2 is 5. So we want to find a point, find C, such that f prime of C is equal to 5. The mean value theorem says that's possible. Well, this is my function, 2x cubed minus 3x plus 1. The derivative, f prime of x, is 6x squared minus 3. And we want that to equal 5, which means 6x squared equals 8. X squared equals 8 over 6, or 4/3. So x is the square root of 4/3, which is 2 over root 3. So here we have a point where the derivative is equal to 5. That's the mean value theorem. And again, as if much of this calculus that we're doing is very simple and clear once you understand it clearly, but it takes an enormous amount of work to get to the point where you understand it clearly. And there's no shortcut for putting in the time to understand the material. What is one very important and immediate consequence of the mean value theorem? Suppose you have a function f prime of x where the derivative equals 0 for all x in the interval from a to b. So suppose we take 2 points between a and b. Listen, I want to make sure I have a good way to express this. So the conclusion is then f of x is a constant function. Let's just say f of x is equal to 0 for all x in an open interval I. Then f of x is a constant function on this interval. See, why is that? So that a and b be points in I, then we can solve the equation f of b minus f of a over b minus a was f prime of c for some c in the interval. Let's say we have a less than b, but the derivative is always equal to 0. That was our hypothesis. We have a function whose derivative is identically equal to 0. So if b is different from a, this has to be 0. So f of a equals f of b for all a and b in the interval. So a function which is always 0 is a constant function, and only the constant function has its derivative always equal to 0. It also follows that if we have functions f and g and f of x and g of x satisfy f prime of x equals g prime of x for all x in this open interval I, then g of x minus f of x is a constant. And the proof is that if we let, let's say, h of x be the function g of x minus f of x, then h prime of x is f prime of x minus g prime of x is 0. So h of x equals a constant. So g of x minus f of x equals this constant. So g of x is always f of x plus the same constant. Okay, well, I don't want to get too far ahead, but we've covered actually quite a bit of material today. That is, there's the Rolle's theorem, the whole idea of absolute maximum and minimum, local maxima and minima, the connection between the derivative and the local and the extreme points is very important. And the mean value theorem is very, very, very important. So the more time you spend studying this and the more exercises in my lab you do, or in the book, the stronger will be your understanding of all of this material. Any questions about this? If not, we will stop now. There's not a review session today because we just had an exam, but there will be problem sessions. I'll post the hours this week, Friday, and also sometime over the weekend. And then the next regular class again is on Monday. Any questions before we stop for the morning? Okay, good. See you on Monday. Bye all.